So let's move to next normal form. That's fourth normal form. And that normal form deals with multi-valued dependencies. Functional dependencies result, right side of functional dependency is something unique. If we know value from the left side, from the key, then only single value is allowed for right key, or for right part of every dependency. So that's functional. And multi-value is not functional. For every value on the left side of dependency, we may have multiple dependents, but not anything, but just a limited list of dependent values. And let's look at example of skills. For each person, we know that that person has different language skills, may speak on different languages, Greek, Latin, German, and know some programming languages, Pascal, C, and Ada, and Ada, and something. We may check this table. Let's look at person number. Person number has multiple duplicates, so person number is not a key. And language has duplicates, and programming has duplicates. So probably, and let's person error and language, this value in Greek, this value in Greek, C and Pascal, not functional. So probably this table is the whole key. In this table is the whole table, just 3 columns. So for tables that consists of key only, let's check first normal form. Yes, it conforms to first normal form or only atomic values. Second normal form, complex key, but no non-key attributes. So, and second normal form speaks about non-key attributes that doesn't belong to any key. So we have no such attributes. So second normal form, this table confirms to second normal form too. Third normal form, about transitive dependencies between non-key attributes. We have no non-key attributes, automatically third normal form. So the whole table is just a key, just complex key. So we store just some combinations of values, and each combination is unique. We don't duplicate combinations, but it's quite complex. So third normal form, we conform it, and Boy's code normal form, the same as third. So we have no non-keys, and we have no functional dependencies, essentially, besides trivial. And the key is a whole table, so that's it. So it conforms to all the normal forms up to fourth, including Boy's code, normal form, third, second, and first. But is it redundant? Yes, it's redundant. So we store Greek twice, Latin twice, and Pascal twice. And what if this person will learn a new language? You need to add, let's say, Java. So we need to add a record Greek Java and Latin Java to follow this structure. So, and then we'll store Greek triple times and Latin triple times. So that's not too efficient, probably. That's why do we need to store just single fact that person knows Java in 2 different records and maybe in more different records. So how to model the same thing differently? First option is to violate first normal form and say that our skills are lists. So this person has this list of languages that it speaks on. So Greek, Latin, and maybe something else. And that programming languages is another list, C and Pascal, and we may add Java there, and that's all. This model would work, yes. We have no redundancy, and mainly no anomalies, and SQL of some versions that's not implementable. And yes, that's implementable in any database using just strings to store language, and I may keep this list in a string and then parse it manually, but such columns can't be used in queries efficiently. So I can't use them as a foreign, so I can't restrict them. I can't say that here's my library, my dictionary of possible languages. And I have record for Greek, Latin, English, German, and something, and Russian. And only these languages are allowed. So I can't say that foreign key from language column to there. I have no Greek and Latin value in my dictionary of languages. The same thing for programming. So I can't use it for foreign keys. I can't use it in joins. I have some table that Greek people who know Greek, who knows Greek language, we multiply, we add some money for their work. Just the salary need to be increased for 10%, just for Greek language knowledge. And we have a table with this percentage. So Greek 10, Latin 12, and Russian 30%. And we can't search language equal to language in that table of extra money, but we can't compare them. We have Greek and Latin and something and Russian here. If we try to compare list to an element, that's not possible. So that's why non-first normal form are being implementable, but that's not a good fit for relational operators. In relational operators, also relational operators expect atomic values to compare them, to essentially implement joins, to implement lookups and everything. So that's why design theory of relational theory that's not quite a good fit to complex nested structure, including XML. Other way, let's not store all the possible combinations. Let's store just few of them. Let's say instead of storing everything, we may say that this person knows Greek and C and Latin and Pascal. So only once we store Greek and some programming language and Latin and Pascal. But if we'll have a request, a query, please find me all the people who knows both Greek and Pascal. So we built a team for a new project that will be created in Pascal programming language, but for this Greek interface for Greeks, about Greek history, about something. So we need people who knows both. Let's check. This person knows Greek and C. No. This person knows Latin and Pascal. No. But that's essentially the same person. And to answer this question, we may need to manually build complex joins. But what if a person has 10 languages and 20 programming languages? So we need, I can't be sure that I need, not can't be sure that's possible, but I need to perform extra work. Some anomalies, what happens if this person learns a new language? I need to add it without maybe programming language paired with it. So some anomalies maybe. What's the problem essentially? Essentially, the problem is this: is that person knowledge of language and knowledge of programming language are completely independent. We don't need to put them in the same table. That's a problem. But so how? And that's a matter of multi-value dependencies. If in a table I can meet such a situation that I have a key, but that's not a key. It has multiple duplicates essentially. So in multi-value dependencies, that's not essentially key. That's just left part of some dependency. And I can use two arrows to say that for every a value, small a, small a, small a, small a, I have a list of b values. So for a, values in b may be b small b or b twice bb. just and nothing else, only something from this. And for C, I may have C or CC and nothing else. So if in my domain, that's correct dependency, and that essentially means that I don't have just unique value for B and unique value for C. I have multiple values for both B and C. So, but I want to keep them. And A became not a key in this case. So, and yes, all the possible combinations of them. So, formally, multi-value dependency, or MVD, take place if and only if and only if I can find two different records in a table, T1 and T2, two different tuples, such that if they have the same columns in left part in alpha columns, alpha here equal to alpha there, then I can find two another records in R with the same alpha columns that's equal to, so alpha columns in all four records and for all four tuples is the same. T3 alpha equal to T4 alpha, to T1 alpha, and to T2 alpha. All the records have exactly the same value combinations. And T3 beta equals to T1 beta. So T1, T2, T3, T4. T3 beta equals, so that's not correct driving. That's not correct picture. Picture doesn't correspond to, so I have first record and the same value here in first and fourth. Anyway, I need to say that T3 has the same as T first and the same value in T2 and so T2 and T4, that's one value combination. And T3 and T first is another value combination. T3, so beta and gamma are changed here. So picture is like this. I have the same value of red color and same values in light, let's say blue color. And same values of red color in this group of columns and light blue value, light colors of the same value of the light blue. So in each column, the same color means the same values. So essentially, for every possible values here, I expect to meet exactly 4 records, not lesser and not bigger. There's exactly this pairing of values. So all the combinations red and red, blue and blue, blue and red, red and blue. And then I can say that I have multi-value dependency in this table. And only in this case, if I can find such a quadruple. So I can say that first number, language depends on first number. But I can't say that language depends on first number functionally. That's not the case. Each person number has multiple languages. And that's exactly the case. First number is defined as corresponds to multiple language values. The same things that first number corresponds to multiple programming values. And let's say what is difference between language and pair of first number and programming. Probably that's that's not a key, but we have dependency. Each time I have, oh no, so that's not dependency. So other columns are not depend on each other. Multi-value dependencies are not symmetric. I can't say that language has multiple dependency to person number, but symmetric multi-value dependencies exist. So we can find examples. So let's look at how to fix it, how to store this information. It's better to store it, let's say, this way. I have table of languages, person number, and language. And the key here is 2 columns. Both columns are parts of a key. So we just project and have this person knows this language, this person knows that language, this person knows this language, and so on. The same for programming languages. This person knows C, this person knows Pascal, the same person. And key here is 2 columns, consists of 2 columns too. And if we join it back, we'll get exactly what we have. So, and if we add, let's say, Java here, we can rebuild this table correctly. So we'll have pairs of Greek and Java, Latin and Java. So structure will not be broken. Another example for drinkers. I have a table that people who have name, address, phones, and a list of beers that people like. So some people may have several phones, address is single, name is single, and name probably key, and multiple phones may have several phones and may like several kinds of beer. So I have functional dependency. Address depends on name, functional. For each name, I have a single address. And for each name, I have multiple phones and multiple beers. Essentially, phones and beers are independent. And I can store them in non-first normal form. But I better to decompose it almost the same way as we decompose it for functional dependencies. I have a table, and I say I split it into 2. One table or R1 and second table of R2, and then the same idea that decomposition is lossless if and only if intersection of columns is a left part of multi-value dependency for both tables. So not just functional dependency like in decomposition for functional dependencies, but multi-value decomposition. And we need to show that if and only if. Let's return to decomposition definition here. Decomposition is lossless if, but we may have decompositions. We have if this, then decomposition is lossless. But we may have another lossless decomposition without this condition. That's not only if this. And here in first normal form, that's two directional. If and only if. And for multiple value, multi-value dependencies, we may have trivial dependencies if the whole table is on the right part. So that's trivial. So if I have a couple of columns, then everything else depends on me trivially. So for every table, if I get some column and say that everything else multi-value depends on me, everything else. So I have no just combinations. To have multi-value dependencies, I need to have 2 columns, and every multi-value dependency come in 2, or essentially in paired. That's paired dependency. I need to have betas and gammas and build combinations of them. If I have just group of columns of beta and gamma is empty, that's not multi-value dependencies. I can't I can't conform to these requirements. So I can't check gammas, and so that's completely different situation. If gamma is empty, I can't build something like this. But if gamma is empty, that dependency is trivial. If I have an alpha, just two records with the same values, and just two different values in beta, or the same just single record and some values, everything is possible. So multi-value dependencies are only for two groups of columns on right side of dependency, and both of them need to be dependent. So anyway, if I have A on left side and two groups B and C, multi-value dependencies is that B multi-value depends on A, and at the same time C depends on A. So it's not possible that B depends and C is not. So to have multi-value dependencies, we need to check this. So trivial dependency is that all the columns depends on left part. So gamma is empty, we may check everything, and that's trivial that it holds. So we may check it. That's quite simple. The same thing we may prove this situation. So from alpha, the whole table depends from alpha, and whole table, all the columns besides alpha may be put to the right side, and it can be proved too. So that's for trivial MVDs. Trivial MVDs are always here. If we have functional dependency, we may say that's just corner case for multi-value. So if beta depends on alpha functionally, then beta depends on alpha multi-value, but somehow it happens that beta has just single value. That's possible. So that can be proved too. But in back direction, it may happen that beta has just single value and then unique value for each alpha value. So we have functional dependency too, but in the common case, that doesn't always hold. So if we have multi-value dependencies, probably this, in most cases, we can't deduce it. So we can't deduce it for sure. So if person number depends, language depends multi-value, has multi-value dependency on person number, but language doesn't depend functionally from person number. And other laws like reflexivity. If beta is subset of alpha, so alpha is set of columns, beta is subset of those columns, we may say that's reflexive function, and it's functional. That's functional dependency, that's trivial functional dependency, and each functional dependency, maybe we may say that due to promotion law, that multi-value dependency does hold too. Augmentation, we may add gamma to the left side and beta and gamma to the right side, so we may augment both functional and multi-value dependencies. Transitivity. So transitive dependency come from here. Complement, and complementary is for multifunctional dependency only. If beta from alpha to beta, multi-value dependency from alpha to beta, that means that at the same time, alpha and all the table besides alpha and beta, so all the remaining columns depends multi-value in multi-value fashion from the same. So that's exactly the situation that if I have left part, a group of columns, some columns that I see that multi-value dependence, all other columns are complementary, take part in complementary multi-value dependency. That's complement, laws of complementary dependency. Multi-value augmentation. We may augment it not by just the same gamma. So add gamma here and add gamma here, and then functional dependency continue to exist. We may augment it not only, and yes, we can augment with the same values, but at the same time we may augment left part with something small, something bigger. If I have delta being subset of gamma, then I may add gamma to the left side and delta to the right side. For functional dependencies, that's not possible. That's not provable. But for multi-value dependencies, that's correct. So I may add more fields to the left than to the right, and that's still whole. Multi-value transitivity. If beta depends on alpha and gamma depends on beta, then they depend. Gamma depends on alpha. And generalization or promotion. So if beta depends on alpha, then beta multi-value depends on the same thing. That's promotion. And other more complex laws like Kali's, alpha to beta, and beta and gamma is a subset of beta, and delta is just new columns that are not in beta. So delta is something new to this dependency. Then we can say that and we have functional dependency. Delta is essentially a new set of keys, and keys only for portions for some columns from beta. Gamma is some subset of beta columns, and it depends on something else. Beta depends on alpha in multi-value way, and we have some columns from beta that depends functionally from something else. Then this subset of columns, gamma, that depends on something else, depends from alpha functionally too. So essentially, we may extract some columns that are unique, that has unique values for that alpha. So alpha functionally, so gamma depends on alpha functionally. Union alpha to beta and alpha to gamma. Oh, sorry, and yes, and then alpha to beta and gamma. So we may combine everything to the right. Intersection alpha to beta and alpha to gamma. We may say not only union, multi-value intersection is possible too. So beta is a subset, is a set of columns, gamma is a set of columns. So we may combine them or find intersection of them. That would be still multi-value dependent. Minus alpha to beta and alpha to gamma, then alpha to beta minus gamma, and alpha to gamma minus beta. That's essentially something like intersection, but so everything with beta and gamma, all the combinations, union, intersection, subtraction in this direction or that direction, everything is correct. Everything is possible. But not vice versa. Union in functional dependency, we may move from different dependencies to union and back. Functional dependency may be split by right part, but not for multi-value. If we have such a dependency, that doesn't mean that we may split it into two rules. In some cases that's possible, but not in the common case. It may happen that only this group of fields is depends on left side, and if we split it, we'll lose this property of multi-value dependencies. So yes, not all rules. Language, two-person number, and programming. And that's yes, for each language, we have multiple combinations of person error and programming. But not language depends to person error. That's not the case. And MVD is not totally intuitive concept, so that's why. But let's look how to build it, and then I try to describe why do we have this. Trivial MVDs. MVD is trivial if beta is subset of alpha, or everything but alpha. So all the columns, but columns from alpha, or is a subset of alpha. Then it's trivial. First definition is classical, and then additional definition. Trivial MVD holds for any relation, so it doesn't bring any new knowledge about relation. Essentially, all the functional and multi-value dependencies come not from data. They come from our domain knowledge. So we know that in our company or in our business, in our situation, we have such dependencies. So that's not possible to combine this and that values. That's not possible by our business rules. And it may be reflected in our data, in our structures of our data in form of special tables. So all the dependencies come from business, from customer of our system, of our database, not from data. So all the dependencies if we may check them, and every possible table will conform to these dependencies. So why do we need to think about them? So every possible relation, so that's not a constraint at all. If they say that A, arrow, A, okay, so we don't need to think about this as a constraint. So trivial dependencies are those. And fourth normal form, how to check it? The table in the first normal form, if and only if, for all the multi-value dependencies. And multi-value dependencies are defined by customers, by business, and not by us looking at some data examples. We may find, oh, we have a table with data. Oh, it looks like they have multi-value dependencies. Maybe yes and maybe no. So that's just an idea. We need to check, go to our customer, to our product owner, to business, and ask them, is it really or not? And only them may answer. So we can check that there is no dependency. If we say, oh, we have no four or combination of four records with different combinations, but only 3 of them. So no multi-value dependencies at all. Okay, great. So not every pair is possible. In language and programming language, that's not possible. If I know this Greek and Latin and Russian and Chinese and Mandarin and something, that's completely independent from other. But let's say we're speaking about, let's say, air flights, and some people, some pilots may fly on some kinds of air let's say Airbuses, A 320, 330, 340. And that's one dependency, multi-value dependencies. Every pilot may fly on multiple kinds of Airbuses. Okay, multiple kinds, not just unique. That's multi-value dependencies. And another dependency is a that pilot may be used on flights in, let's say, Monday and Tuesday and Saturday. So that's another multi-value dependency. And then essentially we need to if all the combinations is possible, then we may store that this pilot and Airbus. Pilot A320, the same pilot A340, the same pilot A300 something. So all the pairs of pilot and Airbus. And another table, pilot and day of week. This pilot flies in Mondays, the same pilot flies in Thursdays, and the same pilot flies on Thursdays, on Saturdays. And then every combination is possible. So that's decomposition. That's decomposition of the whole. If we store it in single table, then we need to store it all the pairs. But what if, and in this case, I have multi-value dependencies. But what if this pilot say, I won't fly on Airbus A340 on Saturdays? Oh, not all the combinations are possible. This Airbus and that day of week, the same Airbus, another day of week, the same. So A1, let's say A1 Monday, A1 Tuesday, A1 Saturday, A2 Monday, and A2 Tuesday. A2 and Saturday is not possible due to our business restrictions. So not all the combinations are possible. In this case, we have no multi-value dependencies, no multi-value dependency, and we need to store all the possible combination as is. So this Airbus and that day of week, this and that, this and that, this and that. And multi-value is only when they completely disconnected, they completely independent. Then I may store them independently and don't store all the combinations. I know that all the combinations are available for me, are possible, and that's it. So multi-value, if I can find a multi-value dependency, that lead to more simple storage. I store just list of Airbuses for every pilot and list all the day week of work days in a week for the same pilots, 2 small tables, and then I can build, combine them in any combination. But if I have additional restrictions, I can't store them in 2 tables. I need to store them in single table and keep only exact corresponding record, corresponding values. And that's my knowledge on what this pilot prefer, what's possible and what's not possible. So I need to store it. So if multi-value dependencies is defined or is determined by business, something that come from, not from data, that come from business, then how to check that my table corresponds to first normal form? I check every and all the multi-value dependencies. Multi-value dependencies, essentially, they tell me that, oh, day of weeks and Airbuses are independent. Okay, so that's essentially what I can hear, what I heard when they told me that that's a dependency. Pilot to work day of week. Okay, and pilot to Airbus kind. So at least one condition. If first condition is trivial dependency, so that's dependency of the whole table or 2 subset of left part. In case of pilots and work days, that's not trivial. Okay, and A is a super key of my table. So, and yes, pilot is probably the super key for my table. And then, and yes, that table in fourth normal form, then it implies that it's Boy's squad normal form that can be proved. So if my table is not, oh, sorry, I'm sorry, for pilots and work days and Airbuses, pilot is not a super key. I have multiple records with the same pilot. A super key is all the keys. So alpha is pilot and workday and Airbus. All of them is a key. So if alpha is pilot, then it's not a super key. So my table with 3 columns, pilot, Airbus, and weekday, day of week, work day of week, is not with multi-value dependencies from pilot to workday and from pilot to Airbus. That's not in first formal form, as alpha, being pilot, is not a super key for the whole table. And I need to, so first normal form is violated. I have dependency, but my table is not, so I check it and check that that's not in first normal form. So how to bring it to first normal form? I may decompose it. How to decompose? I start with the whole table, and then I check all the tables that are not in first normal form that can be checked using this checks. I search for trivials and for super keys in the left part, and then find functional multi-value dependency that's evil, that is violated. And probably alpha is not a super key in this case. And then I do essentially the same thing as in decomposition for third normal form. I get everything, all the columns in a dependency, and put it in single table. So let's say pilot and Airbuses depends on pilot. So I create a table, first table with pilot and Airbus, and that's it. And second table is everything that's left after extraction of Airbus. So pilot and day of week, that's second table. And then I remove table from result and add this. So I change it into, I remove original table and add two new tables. And then check for first normal form. In if some dependencies are still violated, so still evil, then I decompose them further. Essentially, operation is the same. The only difference with the decomposition algorithm for third normal form is the kind of dependency. In third normal form, in Boy's Code normal form, I have just functional dependency, and here I have multi-value dependency. So we may draw it this way. So if I find multi-value dependency here, and then the same key and everything else put here, but the whole table has the same alpha as a key, and everything else is a multi-valued key. That's not a key. That's just left part of multi-value dependency. It may have duplicates and need to have duplicates in this table. So that's a part of key. So let's look at an example. I have such a table for a system, person number of assistant, name of that person, name. Sorry. Name of that person, area or topic for PhD or something, professor, language that assistant speaks, and programming language it knows. So that's it. And I may, and I know that boss depends on person number, area depends on person number, name depends on person number. There is no dependencies between areas and bosses and everything, and language, multi-value depends on person number, and programming language, multi-value depends on person number. So each person knows multiple languages and multiple programming languages. So synthesis algorithm led to this thing. So I have just functional dependency from person number to name, to area, to boss, nothing, no transitive dependencies. So I extract them in single table for assistant, key of person number, and everything that depends on it. And put everything else to other table. And in this table of skills, I have complex key that consists of person, language, and programming language. So, and here third normal form stops. So we have no functional dependencies to check, and table that consists of a key columns only. It's in third normal form and in voice code normal form. So we don't that can't violate any normal form rules. But if you want to go further, we look at this table and understand that. So they told us that we have multiple value dependencies from person to language, and from person to programming. Oh, we have multiple value MVD. Let's check. This table violates MVD as personer is not a super key, but by definition of first normal form, left side in multi-value dependency need to be a key. So I have dependency from personer to language, and in skills table, personer should be a super key. That's not a super key. So we violate this dependency and that dependency. So we go to decomposition algorithm and build a table for each dependency. So we extract personer and language into one and remove language. So we have personer and programming that's remain as remaining columns here. So that's the result. And if we check functional dependencies now, then we have so table with personer and language. Let's look at first normal form. Alpha to beta is trivial. And yes, alpha to beta is trivial, as alpha is a person number, beta is language, and let's check what's trivial. First situation, beta is subset of alpha. That's not the case. And beta is all the other columns but alpha. That's the case. So alpha is person number and beta is language, and nothing else in our table. So this table conforms to first normal form due to the fact that it has only trivial dependency from person number to language, and that's trivial. The same thing here, first number to programming, and that's trivial. So first normal form allows to decompose further. It decomposes in more tables than third normal form, and third normal form doesn't recognize multi-value dependencies. That's the situation for multi-value dependencies. And once again, multi-value and functional dependencies defined only by business, not by data, not by data examples. They come from business requirements, and they need to tell you that we may skills in language skills and programming skills are independent. Okay, so they are independent, we may store them independently. Great. But if they say, oh no, we need people who program in Java, we need them to know Greek language. So, and Greek language with Java as skills we want. And let's say Latin in Java, that's not completely not the case. We don't want such people. We don't want persons who know Java and Latin language. So not all the combinations are possible. No multi-value dependencies, and skill table need to contain only allowed combinations. And we can't decompose it, so we'll lose this knowledge if we decompose it. And summary of the whole thing. Summary is this. So we have lossless, first normal form. Almost all the tables, so we have all the tables, even in non-first, with non-atomic values. That's the whole space. Some of the tables are atomic, with atomic values. That's first normal form. Some of them are conforms to second normal form. Not all of them. Some of tables are only conform to first normal form. Some of them conforms to second normal form. Some of them conforms to third. Some of them conforms to boys code, and some of them conforms to fourth. So there's no intersection. We can't have some structures, some tables that conform, say, to fourth normal form and second, but not third and boys code. So that's a hierarchy essentially. And up to third normal form, we have functional dependencies, lossless decomposition, and preserving dependency decomposition. That's synthesis algorithms that lead us to third normal form. To boys code normal form and fourth normal form, decomposition algorithm lead us preserving only lossless. Dependencies are not preserved by this decomposition, and the essence of the algorithm is the same. The decomposition algorithm to boys code and fourth normal form is the same. Let me quickly find it. This is algorithm, decomposition algorithm for fourth normal form. Is checking multi-value dependency. And let me find boys code decomposition algorithm. Here it is. Exactly the same code, exactly the same pseudo code. The only difference is here, only single arrow, and that's all. Only functional dependency. So algorithm is the same. The only thing is what dependencies we check. And and then process of decomposition is the same. If dependency is found, everything in that dependency became new table, and so on. And in fourth normal form, just check for non-functional, but for not for functional, but for multi-value dependencies. It's the same actions if you found such a dependency. That's summary. Yes. Oh, we don't need to perform these exercises here. I'm sorry. And yes, you may try this to find everything, all the dependencies, multi-value, and we may see that Sophie has a multi-value dependence. It has the same father. So from child to father, we have single value dependencies. To mother, single value dependencies. But to grandfathers, different with multiple values, and to grandmothers, multiple values. So we need to think about it and try to decompose it. That's one thing. And let me show what should be done. Oh, I can't show what should be done, as what should be done is what should be done belongs to different people, to different groups. So that's it. That's final thing about normalization, and then we go to other topics. So that's it. Thank you, and have a nice everything.